Over the last few weeks, we were basically studying the principle of operation of a few specific kind of lasers that cannot be grouped as gas, liquid, or solid state lasers. But nevertheless, this specific group of lasers have made a profound impact as far as applications of lasers are concerned. The last laser that we study in this group is semiconductor lasers, the smallest of all the lasers that have been operated till date. Interestingly, such small size of these lasers have actually led their emergence as one of the most popular lasers today. You see, the intrinsic small size of these lasers, of these semiconductor lasers, has made possible its ready integration with other devices. This has primarily led to the explosion of research activity across the world to perfect the dart laser technology by exploiting the unique properties that a semiconductor is known to offer. By the way, semiconductor laser is often called dart laser. That is because the active material for a semiconductor laser is a PN junction, which, as you know, if appropriately biased, perform like a diode. And that is why semiconductor laser is often called also a diode. Now, this feature has led to the emergence of diode lasers as the undisputed leader in the world of lasers. And as a matter of fact, today, diode lasers have made profound impact in our day-to-day life. They are present everywhere. CD players, DVD players, barcode readers, laser pointers, cell phones, high-density television, and the list goes on. The invaluable contribution of semiconductor lasers to humanity is the all-optical fiber network. Undoubtedly, this is the priceless gift of lasers to humanity. This serves as the backbone of today's communication infrastructure for both short and long distance communications. This technology enables near almost instantaneous connections across continents, bridging vast distances just in the blink of an eye. You see, today, you take a mobile phone and establish a video or audio call to any individual, be it your friend or relative, located anywhere on the globe, in just a blink of an eye, irrespective, regardless of their location. They can be located anywhere on the globe. In order to be able to appreciate the working of diode lasers and their diversity and versatility, it is essential that we gain an insight into the physics of semiconductors. I would therefore, in the beginning of this course on semiconductor lasers, would introduce the underlying physics of working of a semiconductor, and I would explain you in a very intuitive and engaging manner to ensure that at the end of this course on semiconductor lasers, you would appreciate greatly the working of semiconductor laser. By the way, the working of semiconductor laser significantly differs from the way a conventional laser operates. But before moving on to the science of semiconductor and semiconductor lasers, it would be useful to look back in history to beginning from the invention of a semiconductor laser and into making them to work like a laser. So basically, we'll journey through the history. You see that certain materials behave like a semiconductor is believed to have been first scientifically documented in the work of British scientist Michael Faraday. He discovered in 1833, almost 200 years ago, that the resistance of silver sulfide decreases with increasing temperature, which is in complete contrast, complete variance to the behavior of metals. These semiconductor materials behave much like insulator at low temperatures, but conduct electricity like metals at room or elevated temperature. As we know, the resistivity of a metal of metals increases with temperature. That means its conductivity reduces with temperature. While as we would see as we move forward in this course, that a semiconductor behaves in totally different manner. That is, with temperature, its conductivity increases. But why the resistivity of metal increases with temperature? You see, metal, as we know, contains free electrons. And therefore, if we apply a potential difference at two ends of a metal, then these free electrons can actually easily flow, constituting a current that will flow through the metal. Because the electrons are free to move, they're not bound by the nuclear force, bound by the Coulomb force, that is the force with which a nucleus binds an electron. Now, as the temperature rises, the atoms in the metal lattice will vibrate more intensely with temperature. That means its frequency of vibration, frequency and amplitude of lattice vibration will also become more. Thus, this vibration essentially hinders the flow of free electron, as it would cause more frequent collisions between the electrons and the vibrating atoms. These collisions would essentially make it harder for the electrons to move freely through the metal and result thus in increased electrical resistance. Consequently, the metal's conductivity would reduce as the temperature increases, because the increased atomic vibration essentially reduces the electron's effective mobility through the lattice. And we would see soon that for semiconductors, it behaves in totally different manner. That is, with increasing temperature, conductivity of the semiconductor reduces. Sorry, conductivity of the semiconductor increases. It, however, took more than a century before the electrical properties of a semiconductor could be manipulated by an American engineer, Russell Shoemaker Old, to build the very first PN junction, which is now ubiquitous. That is, it is present in electronic and optoelectronic devices everywhere. The PN junction, when suitably biased, behaves like a diode and is regarded as the very first semiconductor electronic device. See, when a PN junction, so this is the PN junction, we'll come to this in a while, but I just show you when a PN, how a PN junction behaves, or when a PN junction behaves like a diode. If you bias it in such a way that you connect the N side of the junction to the negative electrode of the battery and P side to the positive electrode. Then a current would flow through this. But if you reverse the polarity, that is, you connect the N side to the positive terminal and the P side to the negative terminal, then there won't be any flow of current. Of course, there will be some residual flow of current. This is called reverse bias current, which is very small. So it conducts electricity in one direction and doesn't conduct the other direction. So it behaves like a diode. So the PN junction, when suitably biased, behaves like a diode and is regarded as the very first semiconductor electronics device. The transistor, that is essentially a variant of the PN junction, that, as we know, has brought a revolution in electronics, a real revolution. And it is not surprising that the 1959 Nobel Prize in Physics was awarded to its 1948 inventors, William Bradford Shockley, John Bardeen, and Walter Hauser Brattain, the Nobel Prize in Physics. It is of interest to note here that Bardeen is the only person till date who was awarded twice Nobel Prize in Physics. His second Nobel Prize in Physics came when he teamed up with his co-workers, Cooper and Schrieffer, when they explained the underlying physics of superconductivity. This, as you know, theory is now popular as BCS theory of superconductivity, Bardeen, Cooper, Schrieffer theory of superconductivity. Well, this was just as a matter of interest. Now, the credit of inventing light-emitting diode goes to Nick Holoniak, an American engineer who in 1962, while working with General Electric, was successful in generating spontaneous red light from a forward bias PN junction of gallium arsenide semiconductors. So what they basically did, such a forward biased PN junction, that is, the P side is connected to the positive end of the battery and N side to the negative end. So in this configuration, they found that under certain operating condition, this emits light all around it. I should rather not draw it like this. The light basically emits from the periphery, the junction. Spontaneous emission. So the light from it travels in all possible directions. We will come to this in more detail as we move forward in the course. So this is called light emitting diode, abbreviated as LED. That means when a PN junction, this diode is forward biased, then under certain operating condition, it can actually emit light. So you make a semiconductor emit light. And incidentally, in 2006, the American Institute of Physics announced 5 most important papers in the journals published by it, that is American Institute of Physics, in the journals published by American Institute of Physics, since this institute was founded 75 years ago. And one of these 5 papers happened to be the applied physics letter paper that Holniak co-authored with his colleague to report the creation of the very first light emitting diode in 1962. So it signifies the impact that this particular work had made in the world. This operation of light emitting diode provided a major impetus to build a semiconductor diode laser. Why? Because by then, by 1962, it was quite well known that the photons emitted by spontaneous emission can be made use of seed photons to initiate stimulated emissions in a population inverted medium, prerequisite for the amplification of light. And because the LED is basically spontaneous emission of light from a PN junction, from a diode, so that means if you can maneuver in the right way, this diode can be made to emit coherent light, nothing but laser. So that would be a semiconductor laser. So the operation of LED provided a major impetus to build a semiconductor diode laser, and by the end of that year, that is, I think within just about 6 months after the discovery of LED, Robert N. Hall, an American physicist, while working at General Electric, New York, generated coherent light from a gallium arsenide diode. So this was the very first semiconductor laser that was operated. And the race to build the diode laser was so intense that almost simultaneously the groups working at the MIT Lincoln Laboratory, Massachusetts, and the IBM T.J. Watson Research Center also reported lasing from the same gallium arsenide diode. Of course, they operated these systems independently. And Soviet Union was not behind either. As in the early 1963, Basov and his associates developed the same gallium arsenide diode laser at the Lebedev Physics Institute in Moscow. So you see, within just few months, maybe within 7-8 months after the invention of LED, 4 groups in the world succeeded in making semiconductor lasers. And as you know, Basov shared the 1964 Nobel Prize in Physics with Prokhorov, also an Russian scientist and an American physicist, for the invention of American physicist Charles Townes for the invention of lasers. So, with this historical background, let us now switch over to the science of semiconductors. That is essentially the basics of semiconductors. physics. This is the conductivity of a material is essentially governed by the mobility of its constituent electrons. It is the electrons which are responsible for conductivity, for a material's conductivity. And in particular, which electrons? The ones that are furthest from the nucleus of the respective atoms. Because these electrons, the electrons which reside in the outermost orbits, are the most loosely bound as they are attracted by the nucleus with the least force. It is the Coulomb force of attraction. Now, to determine the energy levels of such electrons, of the isolated atoms, when they are brought closer and closer to form a solid, we consider the simplest case of two hydrogen atoms separated by a distance r. But before we do that, let me very quickly refresh our memory on the way electrons are distributed among various energy levels. Let us consider two cases. That is, consider two atoms. One is hydrogen atom, which is the simplest of all atoms, as it has only one proton in the nucleus and therefore only one electron. That is hydrogen atom. And suppose sodium, which has an atomic number of 11. That means its nucleus has 11 proton. Its nucleus has 11 proton and so 11 electron. So let us see how these electrons are distributed among various energy levels. So for hydrogen atom, this is the nucleus and there is only one electron which is rotate around its nucleus. This is the electron and this is the nucleus which has one proton. So this electron, now we know that the electrons can reside only in some discrete orbits which has also discrete energy because the energy is quantized. So if this is n equal to 1, then we know for n equal to 1, the corresponding value of L is 0. L can have only one value, which is 0. For each L, there can be 2L plus 1 subshell. So for L equal to 0, the number of subshell will be 1, which is identified as S subshell. And the total number of electron that can reside on one subshell is given by this number, 2 into 2L plus 1. So for S subshell, which is L equal to 0, so the total number of electrons that can stay is 2. So here 2 electrons could have gone, but only one electron is there. So we will call it N, that is principal quantum number, A1, then value of S is, L is S, and then we have one electron. Now for sodium atom, there are 11 electrons. This is sodium. So the first orbit, which is n equal to 1, once again like hydrogen, it has for n equal to 1, this is the S subshell, and of these 11 electrons, this has, there can be 2 electrons, because for S, L equal to 0, So total number of electrons that can go into this is 2 into 2l plus 1, which is equal to 2. So 2 electrons goes there. Then the next principal quantum, which is n equal to 2. So L can have the value 0 and 1. So 0 means, once again, the subshell will be denoted as S. So in this, once again, 2 electrons can go because it is S subshell for which L equal to 0. So we will call it 2 is the principal quantum number, 2s2. Then for this principal quantum number, the next subshell has the value L equal to 1. So which is denoted as subshell P. So where, because L equal to 1, so total number of electron that can go in P subshell equal to 2L plus 1, which is equal to 2 into L is 1. So 2 into 1 plus 1. So 6. So then in this, there will be 6 electrons. 1, 2, 3, 4, 5, 6. So we'll call it 6, 2, 2, P6. So then this is 2s2, this is 1s2. So 2 plus 2, 4 plus 6, 10. 10 out of these 11 electrons are already gone to their respective places. Then only one electron is left. It goes into this third principal quantum number, that is n equal to 3. So this is the S subshell and there is only one electron. So 3s1. So you see, this is how electrons are distributed among different shells and subshells. So now let us return back to our problem. That is, we want to determine the energy level of the electrons of an isolated atom, and we want to see how these energy levels are affected as we bring closer and closer another atom to form a solid. To understand this, we first consider the simplest case of hydrogen atoms separated by a distance of r. So I end here today, and in the next class we'll begin from here and we'll see how the energy level of an isolated atom is affected as we bring the atoms closer and closer and pack them together to form a solid.